Okay, so we are going to now look at bases other than E. So the natural base is going to be the easiest way to, the easiest logarithmic or exponential function to take the derivative of or to integrate. But we can also do derivatives and integrals when we have um, a base other than the natural base, other than E. So if we remember the change of base formula from precalculus, log base A of B, we can pick any base we want. And we can do, so if I do log base, just pick some other constant, log base C of B, whatever is we're taking the log of is in the numerator, and then log base C of whatever the base was. So I'm just going to let me go through these. Okay. So log base A, log base C of A, and then log base A of B. So log base C of B. Which is wonderful that we can have that change of base with log any base, but we still are having an issue if we don't choose wisely. So if we're going to do a change of base and we already know how to take the derivative of a natural log base E, natural log, then why not just choose, why did it do that to me? Ln of B, ln of B over ln of A. So here, if I have log base A of X, that means if I do my change of base formula right here using natural log, that means that this will be ln of X over ln of A. And this base A is a number base. We're not going to have a variable base. So log base 2, log base 7, log base 14, log base number, ln of a number is just a number. So this ln of A is a constant. So I can rewrite this as 1 over ln of A times ln of X. And now I can use the constant multiple rule to take the derivative. So if I wanted to take the derivative of log base A of X, what I am basically going to be doing is taking the derivative of 1 over ln of A times ln of X. So I'm using the constant multiple, which is just the, why does it keep showing that at the bottom? It's not supposed to do that. Anyway, which is a constant multiple, trying something new and it's driving me crazy. And now my pen is not working. Oh, typical. There we go. Okay. So again, this was a constant. So just like if I had 2 times ln of X, the constant is just is not part, I don't take the derivative of the constant. It's just multiplied out. So this derivative is going to be the constant, 1 over natural log of A times the derivative of ln of X, which is 1 over X. So I can either write this as 1 over X times ln of A if you are worried about it wondering if the x is inside the natural log, or if you wanted to write it as the constant times x, I can see it that way. Either way says the same thing, just making sure that the x doesn't look like it's inside the natural log. So what that tells me is the derivative of log base a of x is just 1 over x times the natural log of a, or 1 over the natural log of a times x. This is my derivative rule for a log of another base other than e. So if I wanted to take the derivative of log base 3 of x, it will just be 1 over x times the natural log of 3, or 1 over natural log of 3 times x, whichever way you prefer to use it. And if you're wondering what happens if I take the derivative, then using this method of log base e of x, which, if we're remembering, ln of x is just log base e of x. We usually use the ln of x notation. You won't see anybody write it as log base e, but if I take the derivative, that means 1 over x times the natural log of e, and the natural log of e is just 1, which gets me 1 over x. So using this rule also works if I'm using base e, just to show that it is consistent. The mathematics are consistent. So, derivative of log base something other than e. What if I have an exponential with a base that is not e? Well, what I'm going to do is I am going to do logarithmic differentiation, and I'm going to take the natural log of both sides of my equation, and then using log properties, the exponent comes out front. So I now have x times the natural log of a. And once again, natural log of a, that is a number. A is a number. So this is a constant. That natural log of a is just a constant. So now when I do derivative, implicit differentiation on the left side, the derivative of the natural log of y is 1 over y, and then I need the chain rule, so multiplied by y prime. There we go. And then when I take the derivative here, I have my constant times the derivative of x, which is 1. So now I have y prime over y equals the natural log of a. And so I want to solve for y prime. So that gets me y times the natural log of a. But y was just a to the x. So now this means y prime equals a to the x times the natural log of a. Or, in other words, if you would like the constant out front, natural log of a times a to the x. So, the derivative of a base other than e to the x, that derivative is just the natural log of the base times a to the x, because the derivative of an exponential is just the exponential if it's e. Derivative of e to the x is e to the x. So the derivative of a to the x is a to the x times the conversion from base other than e using natural log. So I have natural log of the base. So when I'm taking the derivative with a base other than e, whether it is exponential or logarithmic, I have natural log of the non-e base as part of the derivative. So if I want to look at the derivative of log of cosine of x, what I see here is cosine of x is an inner function. So this is going to get me a chain rule. So y prime is going to equal, this is log base 10 if the base isn't written. So I have 1 over ln of 10. And then I'm going to take the derivative. Derivative of a log is always 1 over. So I've got 1 over cosine of x. And then I need to multiply for the chain rule by the derivative of the inner function. So the derivative of cosine of x is negative sine of x. To keep it as a fraction, I'm going to write it over 1 so that I can then see I have negative sine of x over ln of 10 times cosine of x. Some of you were like, well, sine over cosine is just tangent. If you wanted to, it is not required. You could say that then this is negative tangent of x over ln of 10. But again, you don't have to do that. You can stop once I have taken that derivative. So what if I asked you to take, find y prime if I knew that y was log base 2 of tangent of x squared. Now this one has 2 chain rules. If you would like to try it, go ahead and pause the video and see if you can find y prime. So because I'm in log base anything other than e, I need 1 over ln of the non-base, the non-e base. So since this is base 2, I have 1 over ln 2. And then derivative of a log is always 1 over what is inside the log. So I have 1 over tangent of x squared. And then inside I have tangent of x squared. So that is going to be multiplied by the derivative of tangent of x squared is going to be secant squared of x squared. And again, so that I keep it as a fraction. And then inside my tangent, I have another inner function. So the derivative of x squared is 2x. So then if I just take all of these and multiply the numerator, I have 2x secant squared x squared. And when I multiply across the denominator, I have ln 2 times the tangent of x squared. And you don't need to do any more simplifying of that one. And now, so those were log base something other than e. So now let's look at an exponential with a base other than e. So here, y prime is going to be the natural log of the base. And this is base 3. And then the derivative of an exponential is just the exponential. And then because I have a chain rule, a function inside a function, I need to multiply by the derivative of that inner function. Now it should make sense that when I have a log base 2 that is brought down, the base is written below, that our conversion is also written below so that we have a fraction. When I have an exponential, then I should see the natural log of the base not in a fraction. if that helps with you seeing it that way. So then let's try this one. Y equals 5 to the secant of x. So if you would like to try to take this derivative, go ahead and pause the video and try that. So y prime, I have to do my conversion to a natural log. So that's the natural log of the base that is not the non-e base. And then I have derivative of an exponential is just the exponential. And then I have an inner function. So my inner function, the derivative of secant x, is secant x tangent x, and they do not have any more inner functions. Technically, I have x, but the derivative of x is 1. So that's where my chain rule after chain rule after chain rule stops. And there's no simplifying of this one. There's no way to write it as just one fraction. It's just written out as the product. So if the derivative of x cubed is 3x squared, then remember the integral of x squared dx, we multiplied by the 3 here, and then when I go backwards from my integration, I have x cubed divided by 3 plus c, so that I multiplied by 3 in the derivative, so I am doing the opposite when I go the other direction for an integral. So if I use that same logic, if the derivative of log base a of x equals 1 over the natural log of a times x, and the derivative of a to the x is the natural log of a times a to the x. Let's keep that in mind as I look at integration. So if I want to integrate a to the x, here what I should notice is that I multiplied by natural log of a in the derivative, just like I multiplied by 3 in the derivative. So going backwards to my integral here, derivative of a to the x is, or derivative of a to the x has that natural log in it, but the a to the x is there. So going backwards, I'm going to have an a to the x. And since I multiplied by ln of a in the derivative, to go backwards, I'm going to need to divide by the natural log of a to undo what would have been that multiplication. And then I need my plus c. Just like we saw with x cubed. If I multiplied in the derivative, then going backwards from that, I had to divide in the integral. So if you would like to try to integrate 5 to the x, go ahead, pause the video. So since 5 to the x was the derivative of 5 to the x, we would have the 5 to the x, but the derivative also had the natural log conversion, so it was multiplied by the natural log conversion. So now I need to divide by the natural log conversion plus c. Now, when we get into exponentials, here's where people start getting confused and maybe make a couple mistakes, because what's the base and what's the exponent matters. So here, the derivative of e to the x is just e to the x. But this next example here, the base is not the number. The x is the base. So the derivative of x to the e, the exponent is e, which is a number. So this is a power rule. So this derivative is going to be bring the exponent out front and then subtract 1 from the exponent. So if I asked you to find the derivative of x to the pi, the exponent is a number. This is going to be a power rule. This will be pi times x to the pi minus 1. It doesn't look like pi minus 1 there. Pi minus 1. There we go. Okay. So the last thing that comes out of exponentials and bases other than e are, and when we start doing exponentials, is the compound interest formulas. So I don't know if you remember these from pre-calculus. What I would like for you to do is pause the video and just see if you remember these two formulas from pre-calculus. Interest compounded n times a year, the total amount of money in the account or total amount going to be paid for the loan is going to be equal to the principal, how much we borrowed or how much we saved initially, the initial investment, times 1 plus r, the interest rate as a decimal, over the number of times it is compounded a year, and then that is raised to the n, number of times it is compounded per year, times the number of years. And then compounded continuously is what we called before the PERT formula. And I said what these letters stood for when I was stating the formula, but A is the total amount either paid back if it was a loan. So if I borrowed $8,000, but when I finished paying off after 5 years, I ended up paying $12,000, that would be the total amount because of what I started with plus the interest. P is the principal, or in other words, the initial amount. R is the interest rate, but that needs to be written as a decimal, not as a percent. So for example, 8% is 0.08 as the decimal. T is the number of years. And then N, which is only applicable in the first equation, is the number of times interest is compounded. That just means how many times they calculate the interest each year. So compounded annually. So if interest is compounded quarterly, then N is 4 because we would compound interest 4 times per year. Or in other words, we would calculate how much interest is earned or how much interest is owed 4 times a year, quarterly. If I were to do it daily, then N would be 365. The nice thing about these formulas is that they are actually derived from calculus. And so when you are given an interest problem and asked to calculate total amount of interest or total amount, principal plus interest, using these formulas is using the calculus because they have been derived. If you would like to see the derivation of these equations, you can let me know and we can go through that. But usually I've found taking the time to derive it is just more confusing at this moment in time than just understanding that these formulas are derived through the calculus.